So now to solve for r, we can use our previous derivation to get the amplitude. And from that formula we derive from r, we can say that r is then equal to the square root of c1, which was going to be minus 1 over 2 squared, okay, plus 1 over 6 squared, okay. And what this is all going to equal to is the square root of 10, all divided by 6, okay, which then equals 0.52705, okay. So you can use either the exact value here or a decimal approximation. And believe it or not, the decimal approximation will often be easier. So now let's get to the phase shift, which was delta. To solve for delta, it's a little trickier, but it's not any harder than using a calculator. It's inverse tangent, and that's going to be C2, which was 1/6, divided by C1, which was minus 1/2. Okay, and therefore this will give us negative 0.32175. And again, the decimal expansion will often be easier here. But I should warn you guys, we need to be careful with this part. The phase angle that we found here, the delta value, is actually in quadrant 4 when you look at a Cartesian plane. But there is also an angle in quadrant 2 that could possibly work as well, okay? So we get the second angle by adding pi to the first angle. So we actually have two angles, okay? So let me show you what those two angles are explicitly. So the first angle, delta 1, is equal to the value we just found, which was negative 0.32175, okay? The other one, the other angle that we have to be watchful of is this one. If you add pi, which is 100 in, literally pi, 3.14189, we get 2.81984. Okay? And so we need to decide which of these phase shifts is correct, because only one will be correct. So to do this, we need to recall that C1 was equal to R times the cosine of delta, and C2 was equal to R times the sine of delta. Okay? So here we are assuming that R is positive, and this means that the sine of cosine delta will be the same as the sine of C1, the constant. And the sine of sine delta will be the same as the sine of C2, okay? So for this particular case, we must have that the cosine of delta is less than 0, and sine of delta is greater than 0, okay? So this means that the phase shift must be in quadrant 2, and so the second angle is in fact the one that we need. Okay, so let me go ahead and repeat that just for a moment, and just so you guys can see exactly what I just said more explicitly. Okay, we are assuming that first of all that R is positive. Okay, we are assuming that R is positive. Okay, and what this means, or what this implies, okay, that the sign, literally the value in front of cosine delta, whatever positive or minus sign is here, will be the same, okay? This sign will be the same, positive or minus, will be the same as the sine of C1. Okay, so coming up here just for a second. So what did we say? R is positive, right? So this value here is positive. So that means the sine of C1 also needs to be positive. Okay, so that's the connection that we can make with that statement. And also, the sine of sine delta will be the same as the sine of C2. Okay, so here sine delta is positive, so therefore C2 must be positive. Okay, therefore, in our particular case, cosine delta is actually going to be less than 0. Okay, and sine of delta is going to be greater than 0. Okay, and so if that is the case, negative values of cosine means we go along this way, along this axis, and positive sine means we go up. And so normally when we talk about quadrants, we say this is the first one, we say this is the second one, we say this is the third one, and we say this is the fourth one, right? So we're looking for a value of delta that puts us right in the second quadrant because of this observation that we're making. And so that being said, we would select the delta value that puts us in the second quadrant. And so that would happen to be delta 2, which is the value where we added pi. And this gave us the 2.819, 8, and 4. Okay. So now that we know which delta to use, based off of that observation we made above, we can now write out the final displacement equation. So after all of this displacement has been computed, we end up with the final grand equation, which is u of t equals 0.5275 times cosine of 6t minus 2.819, 8, and 4, right, from above. That would be delta 2 right here. Okay, and so we can sketch this equation, as you should too, and please use a graphing calculator for this. We can show the displacement for the first 5 seconds for this system. So after 5 seconds, we have the following. Let's go ahead and draw this out. We have t here along the x-axis. We have displacement here as u. Comes up here to about 0.5. Let's see, halfway marks roughly here is 0.25. Okay, and we can go down a little bit more here. We can have a negative 0.25, and we can have negative 0.5, right? Okay, so the way displacement works then here is time. Wise, we have 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, right? And so it's going to come up here and then come back down. As you can imagine, this is going to oscillate back and forth um, in such a way that is not completely clear here. Let me go ahead and redraw that. Okay, so let me try this again. Comes up, comes down like this. This is actually the accurate picture here. It comes up, comes down, just like that. Comes up, and then comes down, just like this. And then once again, same process, same rhythmic motion over and over and over again. Okay. And so that would be the chart that you would expect for this equation. Okay. And that's how you would conclude in solving a situation where you have free and undamped motion. And so in our next session, we're going to talk about free and damped vibrations.